Operating systems manage memory allocation to ensure efficient use of the computer's memory resources. They provide mechanisms to allocate memory to different processes and applications while preventing them from interfering with each other. The operating system's memory manager keeps track of which parts of memory are in use and which are free, allocating and deallocating memory as needed. Dynamic database handles frequent updates and changes. Static database stores data that doesn't change often. Static memory allocation. Memory is allocated at compile time before the associated program is executed. The size and location of memory are determined during the compilation process, typically used for fixed-size data structures and variables. Example: arrays with a predetermined size. Dynamic memory allocation. Memory is allocated during runtime when the program is executing. The size and location of memory are determined as needed, allowing for more flexible and efficient memory usage. Example: using functions like malloc, calloc, realloc, and free in C, or using operators like new and delete in C++. Memory allocation functions. Malloc, memory allocation, allocates a specified number of bytes and returns a pointer to the allocated memory. Calloc, contiguous allocation, allocates memory for an array of elements, initializes them to 0, and returns a pointer to the allocated memory. Realloc, reallocation, changes the size of previously allocated memory. Free, deallocates previously allocated memory. Key concepts in memory allocation. Heap, a region of memory used for dynamic memory allocation. Stack, a region of memory used for static memory allocation, typically for function call management, local variables, and control flow. Memory leaks occur when allocated memory is not properly deallocated, leading to wasted memory resources. Fragmentation, memory can become fragmented over time, leading to inefficient use of available memory. Understanding memory allocation is crucial for optimizing program performance and ensuring the efficient use of system resources. Virtualization involves creating virtual machines, VMs, that emulate physical computers. Each VM can run its own operating system and applications, providing strong isolation and flexibility. If we treat each VM as a component of a horizontal partitioning system, we can design a dynamic and static database without relying on external SSDs. Multiple VMs can run on a single physical machine, sharing the underlying hardware. Horizontal partitioning, also known as sharding, it involves dividing a database into smaller, more manageable pieces, each stored on different VMs. Each shard holds a subset of the data, typically rows, based on a specific partitioning key. VirtualBox, an open-source option for personal and professional use. Hyper-V, a Microsoft product integrated with Windows. Containerization uses containers to encapsulate an application and its dependencies, ensuring it runs consistently across different environments. Steps to implement. Setting up virtual machines. Use a hypervisor, e.g., VMware, VirtualBox, KVM, to create multiple VMs on a physical server. Allocate sufficient resources, CPU, RAM, storage, to each VM based on workload requirements. Database installation. Install and configure a database management system, DBMS, on each VM. Examples: MySQL, PostgreSQL, MongoDB. Data partitioning. Design a partitioning strategy to distribute the data across VMs. For horizontal partitioning, decide on the partition key, e.g., customer ID region. Ensure that each VM handles a distinct range of data. Dynamic and static data management. Dynamic database VMs allocate specific VMs to handle data that requires frequent updates. Optimize these VMs for write performance. Static database VMs allocate other VMs for static data. Optimize these VMs for read performance and storage efficiency. Data distribution and access. Implement a routing mechanism to direct queries to the appropriate VM based on the partition key. Use a load balancer to distribute requests evenly and ensure high availability. Synchronization and consistency. For dynamic data, implement replication or synchronization mechanisms to ensure data consistency across VMs. Use database tools and frameworks that support sharding and replication, e.g., MySQL cluster, Cassandra. Monitoring and maintenance. Continuously monitor VM performance and resource usage. Scale the system by adding or removing VMs based on demand. Perform regular backups and maintenance to ensure data integrity and availability. Advantages. Scalability. Easily scale by adding more VMs to handle increased load. Isolation. Each VM operates independently, providing strong isolation and fault tolerance. Resource optimization. Allocate resources dynamically based on the needs of dynamic and static data. Regarding the site and database host. An open-source solution that provides flexibility, scalability, and strong integration capabilities would be ideal. 1. Kubernetes. Scalability and flexibility. Kubernetes can easily manage multiple VMs, enabling horizontal partitioning, sharding, for the database. Container orchestration can efficiently run containerized versions of PostgreSQL, the Python applications with SQL Alchemy and Blender instances. Integration can integrate with cloud services, AWS, Google Cloud, Azure, for additional resources and scaling. Blender as a backend service. Deploy Blender in containers and expose its functionalities through APIs. Management. Kubernetes offers advanced scheduling, self-healing, and load balancing features. 2. Docker Swarm. Simpler than Kubernetes, easier to set up and manage while still offering robust container orchestration. Integration with Docker can use Docker containers for PostgreSQL, the Python applications, and Blender. Scalability supports horizontal scaling and partitioning. 3. OpenStack. Infrastructure as a service. IaaS provides more control over the underlying infrastructure, useful if need customized setups. Database management can host various database solutions, including PostgreSQL. Virtual machines, VMs allows running multiple VMs for different components, useful for horizontal partitioning. Blender hosting can deploy Blender on VMs and interact with it via APIs. 4. Proxmox will likely choose the source. Virtualization platform combines Fir'Mv hypervisor and LXC containers, allowing to run VMs and containers on the same platform. Resource management efficiently manage and allocate resources to different VMs and containers. Database hosting can run PostgreSQL and other databases in VMs or containers. Blender integration deploy Blender instances in VMs or containers and interact via APIs. Fir'Mv hypervisor and LXC containers are technologies used in virtualization, but they operate at different levels and serve different purposes. Fir'Mv hypervisor. KVM, kernel-based virtual machine, is a type of hypervisor that allows the Linux kernel to act as a virtualization layer. It turns the Linux kernel into a Type 1, bare metal, hypervisor. KVM enables you to run multiple virtual machines, VMs, on a single physical server. Each VM has its own operating system and is isolated from others, which means each can have different OS versions or distributions. KVM works by utilizing hardware virtualization features provided by CPUs, like Intel VTX or AMD. It consists of a kernel module, kvm.ko, and processor-specific modules, kvmintel.ko or kvmamd.ko. Suitable for running full-fledged virtual machines with their own OS. It's used for server virtualization, creating isolated environments, and testing different OS versions. LXC containers. LXC Linux containers is a lightweight form of virtualization that provides operating system-level virtualization. Containers use the same kernel as the host operating system, but run in isolated user space environments. LXC allows you to run multiple isolated Linux systems, containers, on a single host without needing to virtualize the hardware. Each container shares the host's kernel, but has its own file system, processes, and network stack. LXC relies on Linux kernel features such as groups and namespaces to provide isolation. It doesn't require a hypervisor since it leverages the host OS kernel for container management. Ideal for running multiple isolated applications or services on a single host. Containers are lighter and more efficient than VMs because they share the host OS kernel, making them faster to start and using less memory. Key differences. KVM provides full isolation with separate operating systems, while LXC offers process and file system isolation but shares the same kernel. VMs using KVM have higher overhead due to separate OS instances, while LXC containers are more lightweight as they share the host OS kernel. KVM is used for scenarios requiring full VM isolation, such as running different OS versions or testing environments. LXC is suited for scenarios needing efficient, lightweight, and high-density application deployments. Proxmox Virtual Environment is a powerful open-source platform that combines both KVM and LXC technologies to provide a versatile virtualization solution. KVM Hypervisor. Proxmox uses KVM to manage virtual machines, VMs. This allows users to run multiple, fully isolated virtual machines on the same physical hardware. Each VM can run its own full-fledged operating system, including different versions or distributions of Linux, Windows, etc. LXC containers. In addition to VMs, Proxmox supports LXC for lightweight container-based virtualization. LXC containers share the same kernel as the host, but are otherwise isolated from each other. This is ideal for running applications or services in a more resource-efficient manner compared to VMs. Unified Management Interface. Proxmox provides a web-based management interface that allows users to manage both VMs and containers from a single console. Resource efficiency. By combining KVM and LXC, Proxmox allows you to use resources efficiently. VMs can be used for applications requiring full OS isolation, while LXC containers can be used for lightweight, high-density deployments. High availability. Proxmox supports clustering and high-availability configurations, enabling you to create a resilient and scalable virtualization environment. Backup and restore. Proxmox includes integrated backup and restore capabilities for both VMs and containers, making it easier to protect and recover your virtual environments. Storage and networking. Proxmox supports various storage solutions and networking configurations, allowing you to tailor the environment. By integrating both KVM and LXC, Proxmox provides a flexible and powerful platform that caters to a wide range of virtualization needs, from heavy-duty VM workloads to lightweight, container-based applications. Proxmox is open source. It is licensed under the GNU Afro General Public License, HPL, v3. This means that the source code is freely available for anyone to view, modify, and distribute. Proxmox the core management platform, is open source. Proxmox Backup Server. This is also available as open source and is used for backup and restore operations within the Proxmox ecosystem. Proxmox Mail Gateway. While it has a community edition that is open source, there is also a subscription-based enterprise edition with additional features and support. In Proxmox you have the flexibility to use both KVM hypervisor and LXC containers, and you control which one to use based on your needs. Choosing between KVM and LXC. KVM VMs. When you create a new virtual machine VM in Proxmox you are using the KVM hypervisor. VMs are suitable for scenarios where you need full operating system virtualization and isolation. LXC containers. When you create a new container, you are using LXC technology. Containers are ideal for running lightweight, isolated applications or services. Proxmox provides a unified management interface that allows you to manage both VMs and containers from the same dashboard. You can create, configure, start, stop, and monitor both types of virtualization environments seamlessly. Separate use. You can choose to use only VMs, only containers, or both, depending on your specific requirements. There is no automatic mixing. You choose what fits your workload best. Use cases. For example, you might use VMs for applications that require full OS functionality and isolation, while using containers for lightweight applications that need fast deployment and lower overhead. Resource management. Proxmox allows you to allocate resources, CPU, memory, storage, for both VMs and containers, and it provides tools for monitoring and optimizing resource usage. Integration. While VMs and containers operate independently, you can integrate them as needed. For instance, you could have a VM running a database service and multiple containers running application services that connect to that database. Flask, Django, and Node.js are web frameworks and environments used for developing web applications, while Proxmox is a virtualization platform used for managing virtual machines and containers. Flask. Type: lightweight web framework for Python. Purpose: used for building web applications and APIs. Features: minimalistic, flexible, and allows for fine-grained control over components. Suitable for small to medium-sized projects or for those who prefer a modular approach. Django. Type: full-featured web framework for Python. Purpose: used for building robust and scalable web applications. Features: comes with built-in features such as ORM, authentication, and admin interface. It follows the batteries included philosophy, which can speed up development for more complex applications. Node.js. Type: JavaScript runtime built on Chrome's V8 engine. Purpose: used for server-side scripting and building scalable network applications. Features: asynchronous, event-driven architecture. Often used with frameworks like Express.js for building web servers and APIs. Suitable for real-time applications and high-performance needs. Functionality: Flask, Django, and Node.js are focused on web application development and handling requests, responses, and business logic. Proxmox is focused on virtualization and managing multiple virtual instances or containers. Use Flask, Django, or Node.js to build and deploy the web applications. Use Proxmox to create and manage virtual environments where you can run applications, including those built with Flask, Django, or Node.js. Technology stack: Flask and Django are based on Python, while Node.js is based on JavaScript. Proxmox operates at the infrastructure level, managing hardware resources and virtualizing environments. Hardware needed: -1 terabyte external hard drive for virtual machines, RAM and resource allocation, and dynamic database operating system. USB for static database storage.